An acidic buffer solution is made up of a weak acid and its conjugate base. When dissolved in water, weak acids form an equilibrium system between molecules of the acid, HA, H+ ions, and conjugate base ions, A-. For example, ethanoic acid in water gives a mixture of ethanoic acid molecules, CH3COOH, H+ ions, and ethanoate ions, CH3COO-. The concentration of H+ and A- ions in the equilibrium mixture will be much smaller than the concentration of HA molecules, as only partial dissociation of the acid occurs. Le Chatelier's principle tells us that once this equilibrium gets established, if H+ ion concentration is changed, then the position of equilibrium will move to oppose this change. For example, if extra H+ ions were added, it would shift to the left, favouring the reverse reaction of A- combining with H+ to try and decrease the H+ ion concentration back down again. The problem is that in the initial equilibrium mixture, the A- concentration is actually the same as the H+ ion concentration. This means the position of equilibrium is equally sensitive to changes in A- and H+ ion concentration. If the position of equilibrium shifts and H+ combines with A- to form more HA, the concentration of A- would start to decrease as well, and the position of equilibrium would have to shift back again to counter this decrease in A-, effectively increasing the H+ ion concentration back up again. As a result, any changes in H+ ion concentration can't really be opposed by the position of equilibrium shifting, and this means the pH of the solution changes significantly if H+ ions are added or removed from it. In an acidic buffer solution, however, the A- concentration in the equilibrium mixture is much, much higher than the H+ ion concentration, and as a result, changes to A- concentration have a much smaller impact on the position of equilibrium than changes to H+ ion concentration. The position of equilibrium is sensitive to changes in concentration of H+ ions and isn't really affected very much by changes in HA and A- concentration. Now, if H+ ions are added to the solution, the position of equilibrium can move to oppose the change and try and get the H+ ion concentration back to what it was before the extra H+ ions were added. It does this by shifting to the left. More H+ ions and conjugate base ions combine to form weak acid molecules. The fact the A- and HA concentrations change as a result of this doesn't matter very much, as compared to their initial concentrations, their change is very small. By keeping H+ ion concentration nearly constant, the solution is minimizing or resisting a change to its pH, as pH is based on H+ ion concentration. We describe solutions that can do this as buffers.